Assalamu alaikum. Today we will be covering an important topic in the electronic devices and circuits. My name is Ayla Safdar. I am lecturer in Mechatronics Engineering Department. The topic we will be covering today is Introduction to the Bipolar Junction Transistors. As you know that transistors has two main types, BJTs and the field effect transistors. BJTs, basically bipolar junction transistors, have two main applications. It can be used for the amplification and it can be used in the switching circuits. We will be seeing the internal construction is of bipolar junction transistors and how the operation of the BJTs. Okay, starting with the BJTs, as we know, have three main regions: emitter, base, and collector. Okay. The First of all, I will differentiate between the diodes and the BJTs. In the diodes, we have only PN junction, one PN junction. While in the BJTs, it is constructed in a way that we have three doped semiconductor regions, each separated by two PN junctions. Okay. We have emitter terminal, we have base, and then we have the collector. As for the types of the BJTs based on the doping, and that is in the different regions, we have NPN transistors and PNP transistors. And as you can see that in the NP transistors, we have you can think that we have a block of silicon. Then we do the doping N type at top. And then in the middle, very thin region P doping. And then we have the highly doped, heavily doped N region. Okay. So the NPN is basically, you can see that here we have two junctions. And this is the base terminal, center one, and this is the collector region, and this is the emitter terminal. Okay. So we have two basically PN junctions. One is between the base terminal and the emitter, so it is known as base emitter junction, which is shown over here. The other one is the PN junction between the collector and the base, which is shown here, base collector junction. So, on the basis of the junctions, whether they are forward bias or reverse bias, we have different. It can act as a switch. It can as an amplifier. Okay, so it is very important to know that whether the junctions are forward bias or reverse bias. So we have here two junctions: base collector junction and base emitter junction. The other type of BJT is basically the PNP transistors. As you can see, only the doping regions they have been swapped. Like we have P, then in center a thin base region which is N doped, which is very lightly doped, and then we have the emitter terminal region which is very heavily doped, but it is of P type doping. So this is the PNP transistors. So two types of BJTs, NP transistors and the ENP transistors. Moving on, it is very interesting factor that mostly students don't know what the term bipolar means in the name of the BJTs, bipolar junction transistors. Mostly they confuse that we have two junctions or like that. So basically, the bipolar refers that in the transistor structure of the BJTs, we use both holes and electrons as the current carriers. So you need to remember that the bipolar term is not related to the two junctions or other. It is basically the current is flowing because of the holes and the electrons. And the PN junction joining the base region and the emitter region, as I told you, is the base emitter junction, while the junction between the collector region and the base region is the base collector junction. Okay. As for the doping, I've in the previous slide I've mentioned again and again, the base region is the lightly doped and it is very thin. As we have seen in the previous on the slide, and you can see this is the base terminal and this is the base region and it is very thin and it is normally very thin and lightly doped. As compared to the heavily doped, we have the emitter region and moderately doping is in the collector region. Depending upon we have NPN transistors or PNP transistors, the doping can be N or P any type, right? This is the basically the standard BJT symbols for the NPN transistor. You can see we have three terminals: base, collector, and emitter. If the arrow is going from base to emitter, you can see here the arrow. It is the NPN transistor. If it is the from emitter to base, then the symbol is for the NPN transistor. So basically, in any circuit, if there is a symbol like this from base to emitter, we have an arrow. You can be known that it is an NPN transistor. Otherwise, it will be PNP transistor. Okay, we will be starting the BJT basic operation. And as I have told that we have two major applications of BJTs. It can be used as an amplifier or it can be used as a switching circuits. So in order to properly operate as an amplifier, the two PN junction must be correctly biased with the external DC voltages. Biasing is very important. If you know that you need to have an amplifier, you need to form BJTs for amplification purposes. So, and using the external DC voltages, you need to correctly bias the two PN junctions. In this lecture, we will be covering mostly on the NPN transistor for the illustration, while the operation for the PNP transistors is same, only the roles of the electrons and holes is reversed. We have bias voltage polarity is reversed, and the current junction are reversed, which I will show in the next slide. Basically, we will be focusing on the NPN transistors, and the operation for the PNP is totally the opposite with the same logic and each and everything. Okay, for the BJT biasing, as I have told you, we have two junctions. Here we have the collector. This is the collector point. This is the base point, and this is the emitter, right? So the junction between the collector and the base is the base collector junction. And for the base and emitter, we have base emitter junction. So you need to correctly bias them for the amplification purpose. In the amplification purpose, we have the base emitter junction forward bias the base collector junction reverse bias. So it is the uh, condition that we have base emitter junction forward bias and base collector junction reverse bias if we want to operate the BJT as an amplifier, right? Okay, you can see here this is for the NP transistor as the arrow is moving from base to the emitter, while this is for the NPNP transistor. You can see only the directions of the current and the voltage polarities are reversed as compared to the PNP, and the overall um, working is same for the PNP transistors, except the polarities, current directions are reversed, right? So we will be focusing on this, and we will do the analysis further for the NPN transistors. Okay, let us examine in the NPN structure. We have heavily doped anti-emitter region, right? In which we have high density of conduction band electrons. Whenever I'm saying the conduction band electrons, these are basically the free electrons due to which the current is flowing, right? Okay, these free electrons will diffuse through. I will show the diagram, then I will come back to the slide. Okay, this is the basically architecture. In a architecture, if I say this is the region, I'm saying this is the emitter region. In the emitter region, we have N type, basically emitter N type. So we have majority carriers, electrons, while the minority carriers we have holes. Okay? The holes are represented by this white hole, while the electrons, which are majority carriers here, are represented by these signs. Okay. Okay. The base region, as I have already told, that it is quite thin and it is lightly doped. Okay. In the base region, as we have the p-type doping, p-type में हमारे पास the majority carriers are holes and the minority carriers are electrons, right? And the third one is the collector, which is moderately doped as it is n-type. So we have majority carriers electrons and minority carriers holes. Okay, how it will be working? Whenever we connect the battery source, you can see that in order to correctly bias them as an amplifier, we have two external voltage supplies. They had one applied at the base terminal and the other one is at the collector terminal. Emitter is basically ground, common ground. Okay. Okay. What happened whenever we connect the electrons from the negative terminal move towards the emitter region, right? It's going upward. As we will, the electrons will push the other electrons, which are majority carriers in the emitter region, and they will be pushed towards the uh, base region. As you can see that we have the base emitter junction forward bias. So this base inclination region is very less, and electrons will easily move on towards the base region. In the base region, what will happen that the as you can see that we have very less doping and lightly doped hai base region. So very less number of electrons will be recombined with the electrons, sorry, with the holes, and they will move outward as a uh, conduction electrons. Okay, so basically electrons that will recombine with the holes in the base region they have shown here. So we have a huge amount of current flowing through the emitter. Very less current is flown towards the base terminal, and the rest will cross. Okay, then we have here the base collector depletion region, which is you can see that we know that base collector junction is reversed by, so we have a large or thick, basically depletion region. In order to understand, it is a question for the students that how the electrons from the base region will move towards the collector, as we have a reverse bias this junction and we have thick depletion region. So the answer is that basically you can see that here we have a large voltage positive polarity, and this voltage source is attracting the electrons towards itself. So the electrons will pass this the reverse bias junction and they will be received by this voltage polarity. The current is flowing that the electrons flow from the emitter towards the base. A very little amount of current is flowing outward from the base, which is IP, and rest electrons will move towards the IC due to the attraction of this polarity. So we have large emitter current, right? Some few of the electrons move towards the base to contribute in the IB, while the rest will move to the IC. In order to understand, this is the description. Uh, I will quickly go through. I have described the all the working operation. A small percentage of the total number of free electrons injected in the base recombine with the holes and move as valence electrons to the base and into emitter as hole current, right? The red arrows that one shown over here, it is talking about this. Okay? When the electrons that have recombined with the holes as valence electrons leave the crystalline structure of the base and they become the free electrons. Most of the free electrons that have entered the base do not recombine because base is very thin. Okay, the main thing is that the free electrons move towards the collector region into the external circuit and return to the base, and this is the whole working. The main point that you should remember that the emitter current is slightly greater than the collector current because some of the small base current, right? So we have the major emitter current, small base current flows towards the base, and rest is the collector current. So you can see that these directions and that have been shown here. This is the electron current movement that we have. Electrons moving from emitter towards the base terminal. So we have the I. Few electrons move towards the base terminal to contribute in IB. Rest electrons move towards the collector terminal, and the IC is flowing through here. While if you can, this is the basically the NPN transistors, and if we have the symbol, it is the same. And for the PNP, you can see the only the current directions are reversed. Other working is same. Okay, the most important formula that will be you will be using in all your analysis of the BJTs, it is that you should remember that emitter current is basically the sum of collector current and base current. right? IB is usually very small in microamperes, while the IC is in milli, and similarly, IA, emitter current, is also uh, the in millis. It is basically sum of IC plus IB. So this equation is very important and we'll be using in different analysis. Okay, let's move on towards the topic that we will be discussing, the BJT characteristics and the parameters that are very important in order to understand the working of the BJTs. Again, this is the same circuit which I've shown earlier. VPB basically is a positive supply applied on the base, and this is the base resistance. This is collector resistance, and we have the emitter at the ground, and this is the VCC, which is a collector positive voltage source applied at the collector terminal. Two important parameters and that play a very important role. We have these DC beta and DC alpha. You can see that beta DC and alpha DC. Basically, the beta DC is the DC current gain of a transistor. It's a simply ratio of DC collector current to the DC base current, which is IC over IV. So this is the most important parameter which is used in the transistor. Based on the transistor, it can vary from transistor to transistor. Typically, it ranges from 20 to 200. It can be higher depending upon the parameters. Beta DC is usually designated as hybrid parameters when you see on the transistor datasheets. Whenever you select a transistor, you should read its datasheet. From there, you can know that what is the beta DC, which will be represented as hybrid parameter HFE. Okay, so you should know that. The other important is parameter is alpha DC. It is simply the ratio of the DC collector current to the DC emitter current. Okay? So we have ratio of DC collector to the DC emitter, DC alpha. Usually this parameter is very less used in the, but you should know about the, as you can see that we have emitter current greater than, slightly greater than IC. So the value of the alpha DC is normally less than 1, and it typically ranges from 0.95 to 0.99 or greater, but always less than 1. In ideal case, when we'll be saying that base current is 0, which is very ideal case, then we can say alpha DC is 1. Otherwise, it is always less than 1. This is a small example that if you have emitter current 100 milliampere and you have base current of 1 milliampere, you can see that it's very small amount. And the IC is 99 milliampere. So the ratio is between the alpha DC IC, which is 99 milliampere, divided by 100 milliampere. So we have 0.9. So it will always be less than 1. Okay, the last example that we will be covering in this lecture is that you have been given that you need to determine the DC current gain. You should know that DC current gain is the most important parameter, which is beta DC, and the emitter current for a transistor, and you have known the IB and IC. Okay, before starting any problem, you should write the basically the formulas, as we have known that beta DC is simply a ratio of IC over IB, right? So you have known IC is 3.65 milliampere, and you have been given IB, which is 50 microampere. When you take the ratio, the value will be 73. So the DC current gain beta DC is 73. Okay, the next thing we need to find is the emitter current, which is IE. As we have learned earlier, that I is simply the sum of collector current and the base current. So we will be use this formula IC plus IB, and we add the 3.65 milliampere into the 50 microampere, and you will get 3.7 milliampere. You can see that it is quite near to the IC, but a very less amount current. Base current is very less. It is normally in microamperes. So you can easily find emitter current and the beta DC using these formulas. Thank you.